subnet. Malhar, after, bro. Okay. Focus here. 145.145.10 0 0 slash 18 slash 18. How many bits on extra I have here? 2. If I want to count how many subnets I can have here, how many subnets? Yuvraj, how did you find that? 2 power 2, good. So it's 4 subnets, it's 2 power 2 because I have 2 extra bits here, right? You see my subnet mask should be 255, 192, and 0. Right, so this is class B plus extra 2 bits here, so 8 plus 8 plus 2 plus 0. Okay, that 2 here, 2 power 2, 2 power n is the subnet bits that I have 2 on extra here. It's gonna give me 4 subnets, right? Now, if I want to know how many hosts I have in here, how many hosts I have in here, what can be the formula? How many hosts? There you go, Bharat. Failed. You failed. You already failed the module, Bharat. Jagjit, good. Good. Yes, Rajvansh, number of host bits. Yeah, tell me. 2 power n. What is n here? Bharat said that it's 2 power 2 minus 2. Is it true? No, it's not true, of course. Right. So what is n here? Jagjit said the right answer. 32 minus 18. Good, Vandan Kumar. Good. Right. So if I take 32 minus 18, okay, I'm gonna find, of course, 14 here. So it's 2 power 14 minus 2. Okay, 2 power 14 minus 2. Be careful, Bharat. This n here is the number of bits of subnets, the extra ones. When they ask you for the hosts, how many hosts, you need to put n here, the number of host bits. Okay, remember, this is my address, a lot of it, right? 32 1 I have. So I took somewhere here on the 18 2 bits and pushed them here, right? This is this n here to calculate how many subnets, right? But if I want to know how many hosts per subnet, this is the bits, the remaining bits that I need to take here as n. I'll be careful with these 2 n's, right? Be careful. He's asking for hosts. Is 14 bits remaining from the 32 minus 18. Okay. So if we do the math, I don't know, there's some calculator here maybe. Two power 14 minus 2 equal 16,382. Here we go. You will end up with this answer here. Okay. Sorry, I didn't know. Yeah, you know it now, right? We explained that yesterday, so you were not focused maybe, or you missed that, but please be careful. It's really important. You need to know what you are doing, okay? Because logically it doesn't make sense at all. If you have the bits of subnets and asking for the host and you tell me 2 power 2, right? Yeah, be careful. Calculate the number of subnetworks slash 17. Slash 17 is easy, right? Is easy. We don't need to calculate anything. We have one extra bit. One extra bit. How many subnets do I have here? How many subnets do I have here? 2. Because of n here is 1, right? So we borrowed 1, we pushed 1, and he's asking for subnets, so I need to put 2 power 1. That is 2. So I have just 2 subnets. I just split it on 2 slash 16. I add 1 extra bit. I have 2 probabilities for this bit. When he's 0, when this bit is 1. That's it. Calculate the number of hosts in the range. So we have 3. 3 doesn't change from 34, 1 to 30. 37 to 54 to 54, right? So if we want to know how many addresses we have from this one to this one, what we should do here? What is my formula? I explained to you this yesterday. So I have, yeah, good. So I have the 34, 34, 35, 36, 37. Okay. So how many times 256? How many times 256? 4 times, right? There you go. You can see my fingers. So it's 4 times. No. Just Quran. Nope. Nope. No, be careful. No, it's 256 times 4, because we are looping 4 times here. Okay, we have all the range, the loop of 30, 34, 35, 36, and 37. So it's 4 times. It's 4 times. In each one, we have 256. So it's 256 times 4. Of course, minus 2, because we don't have the 0 and we don't have the 255 here, right? So it's a minus 2 here. That's gonna give us something, 256 times 4 equal minus 2. It's 1022. Right? Did you get it? Just Quran? Doesn't make sense, all what you were saying here, right? But you get it. It's looping. If I have, for example, this is 34 minutes, and imagine that in each minute I have 256 seconds, not anymore 60 seconds, right? So from the minute 34 till the minute 37, how many seconds I have in between? I have all the minute of 34, all the minute of 35, 36, and all the minute of 37. But inside each minute now, I don't have 60 seconds. I have 256 seconds. So if I want to know the wall of it, it's 256 time 4. But we are starting from 1 and we are finishing on 254. So we are not taking the 255, we are not taking the 0. We should do minus 2, right? In the 34. No, you have it. All the 34. We're starting from 1. 34 1, 34 2, 34 3, 34. So the 34 is included. Yeah, starting from 1. You just do the minus 2 because you delete the address 0 here. We are not starting from 0. Right? But the 34 is included. Don't tell me not in 34. I have all the wall of the 34 is included because I'm starting with 34 1, 34 2, 34 3, 34 4. So I'm taking all the 34 with me, right? All its content. You got it? Just Quran. Got it? Good. So the 34 is included. Be careful, right? It's included here. So we exclude just two addresses, the 34.0 and the 37.255, because when we do just this, we include all the probability from 0 to 255 in each one, the 34, 35, 36, 37. We are including from 0 to 255, from 0 to 255. But here from 1 to 54, so we need to exclude these two situations to get the right answer. Calculate the IP range of the fourth subnet. Okay, let's do some subnetting here. Step by step. What is the first thing that I need here? Come on, guys, help me. 142. So it's saying here that we have this address 142 82 156.0/27. What is the first step? Find subnet mask. Good. Good, Davinder, Vandan Kumar. Good. I need to find what is my subnet mask. This is the first thing that I have to do. Okay. So I was in /24. Now I'm on /27. How many bits did I provide from the host to the network? 3 extra. Good. So it's 8 plus 8 plus 8 plus 3, something like that. It's gonna give me 27, right? So tell here is 24 plus 3, 20, 27. So this one is 255, 8 is 255, 8 is 255, and the 3 here is 220, 24, of course, right? So now I get my subnet mask. That's good. Now I need to know what is my block size. This is the next step. What is the equation or the formula to do that? Good. 256 minus 224. So I'm going to find a number here that we name it block size. It's going to be 32 in my case, right? 32 in my case. Till fourth time. 97, 126. Good, Davinder, good. Right, you get it from the end. Good. Well, we're gonna go step by step for the others, right? Here now, I need to increment with 32. I know that I need to increment with 32. In which position should I increment in my address here? Which position should I increment in my address here? I do increment here or here or here or here. So first, second, third, fourth. Janish, the fourth. Jagjit, fourth. Others, fourth. Harmander, fourth. Why the fourth? Why the fourth? What is the role for that? Remind me. What is the role for that? Why the fourth? Weird subnet mask number. Good, right? So because of that weird number is on the fourth position in my subnet mask. If it was in the third, I will increment here. If it was in the second, I will increment here. Okay? So it's in the fourth position. I need to increment in the fourth position of my IP address. So 142, 82, 156.0. This is the subnet 0.32. This is subnet 1.64. This is subnet 2 and plus 32.96. This is subnet 3. So subnet 3 is the fourth subnet here, right? First, second, third, fourth. Oh, this is my fourth subnet. Okay. So calculate the IP range here. It's saying IP range. So I need to know what is the network ID. Okay, we got it. This is my network ID. So the network ID, we're gonna tape it here. Something like this. So net ID is 96. This is the fourth network, right? First address gonna be 97. And how I should know now what is the broadcast and the last address? How I can get that? Come on. How I can get what is the broadcast and what is the last address here? One before the next. Explain yourself, just Karan. What this means? One before the next. -1 from the fifth subnet network ID. Good, good. So I need to know what is the fifth network ID, the fifth subnet, to do -1 to find the broadcast here, right? So the fifth subnet 96 plus 32, it's gonna give you 128, right? 128. So -1, 127 here, broadcast. $127. Of course, last address, it will be 120, 126, right? Now be careful, just Karan, it's not 31. You are doing +1 here. You get to 30 and 31, right? I'll be careful. It's minus. You go back. This is the extra fifth one, but we need to identify the range in between here, right? So this is why I minus it, not plus it, right? So minus the 128. I go to 127, and yeah, you detected from 132. No. 96 plus 32, it's 128, not 132. It's okay. Next one. Find the prefix /19. How many bits we did add here? Now those things are easy for us, right? We don't need to do any math or whatever. 19 from 16 to 19. All right, so it's 8 plus 3, right? 16 plus 3, and the 3 we know that it's 224 in the third position right here. So the right answer is 1 here, right? There you go. /21 should be this one, maybe. 8 plus 8, 16 plus 4, 20. No, this is 23. This is 21, right? This is answer 2. 16, 8 plus 8, 16 plus 4, 20 plus 1, 20, 21. Here it is, my /21 right here. Calculate the network ID of the fourth subnet. Okay, let's do subnetting. All right, I have the address 145.12.30.0/21. /21. If in exam we have two options, one with the net ID and broadcast and one without net ID and broadcast, which one is correct for question 4? For question 4 here you mean on the exam? No, if in the exam I will just tell you what is the IP range or the valid address. All I need is this. I don't need network ID. I don't need the broadcast, right? But if I tell you, give me the range, not IP range, just the range of it, right? I need everything. Well, the questions will be clear. I will not trick you in something stupid like this, right? So don't worry about that. Calculate the network ID in the fourth subnet of this /21. We are on /21. /21, how many extra bits I have here, guys? How many extra bits I have here? Come on. 5. Good. I have 5 extra bits. So I have 8 plus 8 plus 5. That give me 2021. So my subnet mask will be 255, 255, 248. Dot 0. Am I good? Is this correct? Yeah. All right. Now I have 256 minus 248. I will end up with 8, of course. So my block size is 8. I know now the number that I will increment with. Where I should increment in my address. Where I should increment in my address. Here is my address. And there is a trick here. Third position. Okay, how should I increment now if I increment in the third position? So basically I need to do this, right? 38.0 and play in place of 30. Good. Be careful. Here, if I need to increment, I need to reinitialize to 0 this spot here, right? I need to reinitialize. Don't just take the number. This is just a tricky question here, a trap. Okay, never increment from the number of that position that you already defined in there. You wipe it. So it's gonna give me 0.0. This is the first subnet. 0.0. And after I will have 8.0. This is the second network ID. Third network ID 16.0. Fourth network ID 24.0. Right? So be careful. Here is asking for the fourth. All right, so first, second, third, fourth. This is the fourth network ID. I already get the network ID of the fourth. Where is it? 24. There you go. So this one is the right answer. Be careful, right? Be careful. You need to reinitialize that position. When you go to increment in any position, if you already find any number in there, you should put it at 0 and start incrementing. So basically, this is just an address here. It's not the whole network. The whole network is 00. You remember, it's /16. This number doesn't have a meaning at all. It's just to trick you. All right, next one. Find the valid IP range of the first subnet. Okay, we can do that. /14. So I have here the address 163.0.0/14. What is my subnet mask here? /14. How many extra bits? It's 8 plus 8? No. Plus 8 gonna give me 16. So plus. Come on, guys. 14/14. 8 plus 6. Good. Come on, wake up. Dot 0 plus 0 plus 0, right? So basically, this is my subnet mask. 255 and 248 plus 4, 252. .0.0. This is the subnet mask. Okay. Now 256 minus 252, it's 4, and this is my incrementation block size. Okay. The number that I increment with is 4. Where should I increment? Where should I increment? Here's my address. 163.0.0.0. This is my first network ID. Where should I increment? In the second position. Good. Because the weird number on subnet mask in the second position. So this is my incrementation position. Okay. Now I should increment here. So it's 4.0.0. 8.0.0, 12.0.0, 16.0.0, and so go on and so go on. He asked for which one? Oh, the first. Okay, so the first is here. I thought he asked for the fourth. Oh, the first is from 1. All right, let's do the first by details. So the first address is 001, right? And I know that the next network ID is 4.0.0. So what is this minus 1? What's going to give me this minus 1? Come on, come on, come on. This minus 1 to find the broadcast of the first. What is the address here? I'm waiting. 3.255.255. Jagjit 254 is the answer, the final answer here, right? Not this one, this one. This is a valid address. I'm looking for the broadcast. My question was just what is the broadcast address of the first one? So this minus 1 is 255.3. So this is my broadcast. Minus 1 again to find the last address, it's gonna give me 254 here. 3.255.254. So this is the right range, is the first one, the first answer. Okay. So I need to find the broadcast first and after go to the last address. Calculate the network submask of /2028. Easy, /28. We have 4 bits, right? /28, 4 bits, 200, 240. 240 in which position? In the last one, of course. There you go. Here's my subnet mask. Okay. I'm adding 4 extra bits. Last question. Calculate the IP address range of the first subnet network. I have 193.0.0./28. We just did it. Here's the subnet mask. Right? 255, 255, 255, 240. 256 minus 240 is gonna give me 16. Right, so this is my block size. This is the incrementation. Where I should increment? 4th position. Here we go. I increment here. Right, so the first subnet is 193.0.0.0. The second one is 16. Right, dot 16 here. Minus 1, 15 is the broadcast. Minus 1, 14 is the last address. Plus 1, 1 is the first address. Here's my range from 1 to 14. Here we go. Here's the right answer. We good? See, easy. The more you practice, the more become automated, right? The more your brain will be trained to do it easily. Also, last network. Well, last network is very easy. You just take this one and replace it on the incrementation number, right? And the last subnet. Okay, I thought I didn't see the question. I thought you want it, right? Well, the last one, you just take this one. Here we go. 192.0.0.240. This is the last network ID, right? The broadcast should be 255, so 254 is the last address, and 241 is the first address. Here we go. Here's the last one. See, the last one, you don't need to increment. You just take that number and you put it in there. It's just a trick, shortcut. I showed you this yesterday. Okay, so this is the last address. All right, and the last one. I need to download it, I guess. Troubleshooting, lab 4, troubleshooting. already exists. Where is it? Ah, yeah. There you go. All right, PC2 able to communicate with PC1. So we don't have any problem in here, right? But not with PC3, not with PC3. Okay, what we can do for that, guys? You see this one communicate with this one. PC2 communicate with PC1 without any problem. See, they are in the same range. And they have just a switch in between them. So there's no problem at all for that. What was the problem? Why this PC2 is not able to communicate with PC3? What is the problem here? PC2 default gateway. That's good, right? Default gateway of PC2. As you can see here, it's not pointed to the right default gateway like this one. Okay. So of course he will not be able to talk through the router. He will not be able to talk through the router because this is the address that should be here, 254, right? Is it correct in this side? Yes, 254, 254, right? All is good. So this is the right answer here, right? So you should correct this default gateway. The problem was on the default gateway of PC2. PC2 is able to communicate with PC3. So now this one is able to communicate with this one, but not with PC1. Why? So he's able to communicate with this one. We don't have any problem here. 50, 0, 1, 200, 200, 50, 50, 0. They are in the same range. 250, 250, 10, 15, 250. The problem is in between these two here, right? Why? Different subnet mask. Good, good. So you see this one and this one here. We are missing a 255 in this one, right? We are on the class C here and should have the subnet mask of class C. Last one, PC1 is able to communicate with PC3. So this one is able to communicate with this one, but not with PC2. Now we don't have any communication going from PC1 to PC2. What is the problem here? Change the network if of PC ID of PC2, the network ID of PC2. So we have here 150, 10, 10, 10, 150, 255. We are on class B. So this is all the computers, right? 150, 10, 10, they are on the same. So this communicate, right default gateway here or not, I don't know. Let's make it bigger. Okay. So they are saying change the network ID of, this is a typo here. Change the network ID, of course, because of this 11 here, should be at 10. This is the first thing, right? So now this problem is solved, but we still have another problem. What is the other problem? Is this basically true here in this question? Is it true? Are PC1 capable to talk with PC3? Default gateway of PC3. Yeah, be careful, right? So 200, 250. Of course. This is just a tricky here. If you analyze, you see that even this communication is not working. Okay. All right. So you guys, you go to Moodle, and I will give you the correction of the exercises here. So, right. And after that, you're gonna find chapter 1, wireless and the exercise of subnetting. Please download that chapter. We find this document here. All right, we're gonna talk about wireless. I did put 3 documents in correction exercises for the corrections that we did together, right? So let's go with the first chapter on this module. It's wireless technology. Wireless, we don't have wires, right? And the notation of the IEEE of all the wireless stuff, we talked about it before. It's a 802.11. Well, first of all, we need to know what is this wireless things, right? How the communication happen in the air? What is really moving? Because there is something that carry data from one point to one point, right? Well, believe it or not, the void that we are living on, it's not empty. Okay, it's not empty. It's the same thing like if you take a fish, for example, in the water. Well, maybe if you're gonna be that fish, you will just see yourself that you are in some kind of empty space. But for us, it's water, right? We see it as water. But in the fish, it's free inside, right? The water is its own freedom, its own void, right? Well, it's the same thing for us, right? When in our space there is waves, but we live in those waves. So it's not the void, complete void. We have many waves, particles that we live on, surround us. A lot of particles. Now, these particles can have some frequency and have some direction and have a wave, right? They are all the same thing. This general wave is the wave of electromagnetic. So it have an electrical field and it have a magnetic field at the same time. So we call it electromagnetic wave. And everything is built basically from this. Everything is electromagnetic with different frequency. That's it. Right. So if you take it, you're going to shape it in other thing. You change that frequency, you're going to shape it in other thing. We have something that's called the wireless spectrum. Here I have just one part of it, right? The big length of the waves, right? We are on 9 kilohertz till 300 gigahertz here. Where we have this telecommunication we use nowadays on the range of frequency. But it's not all of it. All of it start from gamma to X-ray to ultraviolet, and after we have all the visible range that we can see the colors, right? Changing the shape of that wave, it can become the sound, the audible decibels that we can hear, and after infrasound and ultrasound, right? And after we have the infrared, and we have the microwaves, And after we have the radio waves. So this is just the radio waves. To see it, it's better to Google it, right? Because there is many images that electro electromagnetic spectrum. So for example, you Google that and you will end up with this here, right? So very well explicit on Wikipedia. You can see this image here. You can understand what I was talking about, right? So we go to the atomic level here in certain frequency of that electromagnetic wave. We have the gamma rays and X-rays and ultraviolet, right? So this is the size of the atoms. This is size of nucleus. This is size of molecules. When you start having the visible here, right? The visible in here between the ultraviolet and the infrared, we have the size of the visible. And after start getting bigger and bigger and bigger, human, butterflies, some insects, and so go on, we are on microwaves. When the wave have a length of buildings and those stuff, we are on the radio frequency, right? Radio frequency. All the wireless stuff are here. Bluetooth, AM radio, your TV, whatever, going through the satellite, the WiMAX, the NFC, the anything wave that we use for telecommunication nowadays are here in this zone, right? Now, if we get this zone bigger, you will understand what is in the document right here, right? So this is the radio field here, right? We have shortwave radio and the radio satellite. I'm talking about this thing, right? But you see that everything is the same. It's just a matter of frequency of that electromagnetic thing. Here you go, a little bit bigger here. See? So you go to gamma, X-ray, ultraviolet, blah, 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 blah. But when we start getting to the radio zone here, we start having this kind of telecommunication. Okay? Start having the telecommunication right here. Okay. Let's go back to the document. All right. So let's see what he's saying here. All wireless signals are carried through the air by electromagnetic waves. The wireless spectrum is a continuum of the electromagnetic waves used for data and voice communication. So even the voice, the phone, GSM, and all those stuff, right? Like absence of photon is equal to darkness. Yeah, you can say that. I don't know if it's scientifically correct what you said, but yeah, because of the dark matter that we have now, right? Yeah, he's right, technically, still right. But it's not the total darkness is not just the absence of photons. Now we discovered that it's the presence of other things in the same time, because the absence of the photons gonna bring other thing. It's just another phenomena that we call it. It's not the absence of something, it's the presence of other thing also, right? The dark matter, how we call it dark matter. This is why I told you I don't know if scientifically it's like 100% correct, but I get you, right? I did understand. Good. All right, so the wireless spectrum spans frequency between 9 kilohertz, right, till 300 gigahertz. This is all the telecommunication here, voice and data. Each type of wireless service can be associated with one area of wireless spectrum. The Wi-Fi that we use nowadays, right? It's between this range. So we use some Wi-Fi here, and we use some Wi-Fi here, and we have some channels in here, and we have some channels in here, right? So when we go to this, you see, this is 1 gigahertz. Somewhere here, 2.4 and 5 gigahertz, right? This is the wireless LANs, the Wi-Fi, WLAN, right? We are just here, okay? So something in between 2.4 gigahertz and 5 gigahertz. So just as with wireless signals originate from electrical current, of course. So we have some electrical concept here that gonna go to a specific device and will be broadcasted through the electromagnetic wave in this range of 2.4 or 5, depend which type of Wi-Fi we are using. And the waves will be transported through the air. Another antenna gonna catch that, and another device the same will reverse the signal to electrical one, right? So basically when we are using Wi-Fi, you all know it, our computers still use electricity. Our CPU is not working with the radio waves, he still work with the electricity, right? So it's just a matter of method of transportation, of transporting data from somewhere to somewhere using wave. So imagine, for example, if I can send a Morse signal on the water, right? So taping with my finger, I can send an SOS on top of water, right? So now these things are weird for people because for us, it's the void here. And we are used to it. Human beings are the brain, the tools, the receptors, the whatever we have in our body. It make us feel like we are living in an empty thing. I told you, same thing. If you put the fish in the water, it's gonna feel the same thing, right? But for us, it's the water because our receptors can have this reception of water. Our body, okay, so we can see it, we can feel it, the water. When you get a fish outside, so the receptor gonna change, right? It's gonna feel itself in the water, right? So it's the reverse of that. But for us, it's the empty thing. It's our living space, it's our living natural environment, but it's not empty at all. So it's the same thing. It's the same thing like if I use my finger in the top of the water and taping an SOS, and you're gonna see waves, right? You're gonna see the waves transported through the particle of water. And here, the waves are just transported to the particles that we have in the air through the electromagnetic wave, through the electromagnetic wave from one particle to another particle. Okay, so this is how we transport data through the air. Okay. Of course, we need antenna for that. Antenna can send or receive, right? So they can send or receive. We use antenna for reception, and we use antenna for sending in the air. The antenna, we have two type of antenna. One is called the Yagi antenna, the other one called Omni one, right? What is the difference? The Yagi, you guys, you all know it. The concept of the Yagi is unidirectional. You remember the antenna that we used to on the roof of the buildings to catch the signal of TV all days, right? That antenna that looked like this. Or maybe you are too young to remember that. Or maybe there's some places still use it, right? Are you gonna find something still in India? Yeah, still, maybe even in here, you can still find it in some roof of homes or whatever, right? You can get the Hertzian channels on it, right? So an antenna like this, right? This is a Yagi. This is what we call a Yagi. Yagi antenna. Yagi antenna is unidirectional, but it's long distance. Okay. Yagi antenna is long distance, but unidirectional. So it need to be pointed exactly to the signal to get it, because its range is limited. It's something like that, right? So it go far. We have some reception, so it should be exactly on that direction. Or otherwise, it can move, so it go out from that. And this is why you go on the roof, and your brother gonna tell you, to the left, to the left, to the left, right? And then what you are looking for the range of the satellite to catch it, right? It's long distance coming from far, but you need to be exactly on that point, right, to get it. So we use it even for Wi-Fi. We use it for telecommunication. I don't know where is my Yagi antenna. Seriously, I don't know where did I put it. There's something here in the box, but you can use it. You can use the Yagi antenna to connect to the internet. You will see a lot more than you see with your router, for example, because you're going to catch farther point, access point. Okay. And every time you're going to change the direction of this antenna, you will see other hotspots available, and the other is going to disappear, and so go on. Okay. So this is the first type of the antenna. I would call them Yagi, also called unidirectional or directional. Unidirectional or directional antenna. Issue wireless signals along of signal direction. This type of antenna is used when the source need to communicate with one destination. Usually we use it on peer-to-peer communication, right? So one source, one destination. Like TV signal to home and so on, right? This is the directional one. You see, we have many types, and the more they go farther, the more the range will be closed, right? The more the range will be closed, and it's free, right? What do you mean by free, Sheikh? I didn't get what is free. What is free? Yagi antenna is free? No, you need to buy it. Or you need to buy it. Right? You can just go in Amazon, for example, and you can order many type of Yagi antenna. Okay, you need to buy it. It's not free. There's no like free shop Yagi. They open the morning and they will give Yagi antenna to people. I mean, you can catch internet. No, it's not free. You can catch internet. How? Maybe he got subsidy from Gov. Oh no, nothing is free in this world, right? So even if you catch internet, you're gonna need a password, because you are catching internet of your far neighbors with the Yagi. That's it. That's it. What do you think? You think that the internet is like the moon, is something that exists in the space, and you're gonna get it? No, you need access, right, through a provider, and that provider have access point somewhere. So it's just technically that you are receiving a very far signal. Now you're gonna need the credential of that spot to get on it. If it's free, you can go in it, right? If it's public Wi-Fi and you catch it, because it's public, people made it free, but it's not free, right? This is how things work. Now you are paying the internet or not. This depend on that access point, if it's free or not. So the meaning of the Yagi antenna is not to use internet free, is to have some kind of communication peer-to-peer, long distance. We use it on long distance, peer-to-peer. He's gonna crack a Wi-Fi password and use it free. Well, good luck with that. Yes, he can do that. It's a bad thing, but technically, if you know how to do it, he can do it. It's up to him. Or he can just pay the bill like everybody, right? Okay, we have omnidirectional antenna. Omnidirectional antenna, or the omni antenna. Omni antenna are more spheric, and you see that they are not long distance at all. So those ones are used more for LAN communication, right? Local area communication with multiple devices that they connect all in the same time. Like this one you have at home, for example, right? This one you have at school. For example, when you go to the classroom, we have access points using this kind of antenna. Omnidirectional. Those are good for connecting devices together and giving access to an access point. Those are good for WiMAX, for example, right? When we use a WiMAX, we use this kind of antenna. All right. So short distance, use it for LAN, right? Short distance used for LAN, multiple devices, designed to connect multiple devices for home, for example, or your router is omnidirectional. Unidirectional or directional or Yagi one, those ones are used for long distance, more peer-to-peer communication, right? The signals that we use for telecommunication, they have properties. They have some properties. Depend on what they gonna emit or where they gonna land up, right? Walls, irons, whatever you see, signal is in the air, right? And we have many objects. We have a lot of objects with different materials. So we need to take on consideration those things, those properties of the telecommunication. So we have material that they are transmissible. So we can have transmission through them. Materials that we can have transmission through them. So the electromagnetic wave passed through it without any problem. We have other materials that they give us reflection. So they're going to stop the signal and reflect it back in another direction with some angle, right? We have refraction, like the water, for example. The water refract everything, especially the light. If you put, for example, a cup and you put a pen on that cup of water, and you will see the pen broke, something like this, and after it will continue in the other half like this, right? So split it by half because of the light is refracted and give this illusion to your eyes in two places. The light is not coming harmony in the same angle, right? So it's this phenomena is called refraction. We have diffraction. The diffraction is, for example, when we meet some tiny small holes that the signal will be diffracted in multiple direction, right? Passing through that wall or whatever. We have absorption, right? Something that absorbs the signal. It will not be reflected back. It will not be refracted in a different angle, but it will be absorbed. This is destruction of signal mainly, right? Signal is destroyed here, right? And we have scattering. Scattering is kind of a reverse of diffraction here. When a signal gonna emit like spheric things, he will explode in all other directions usually, right? So all these phenomena exist around us with the electromagnetic wave. So the electromagnetic wave work with this phenomena. The frequency range that we use in our Wi-Fi, we use the 2.4, we use the 5.1. The 2.4 is exactly starting from 2.412 gigahertz and going till 2.484 gigahertz. And in here, they splitted it on 11 channels in almost all the countries. Others, they use till 14 channels, right? But usually it's 11 channels. When you go to the property of any network card, Wi-Fi network card, you can choose which channel you want to work, in which specific frequency range, see? So at least every milli gigahertz here, 10 of them, we jump to another channel. And the standard is usually 11. In some countries, they use till 4, right? Some countries, they use till 14, sorry, not 4. So this is the first range of the Wi-Fi. A higher frequency We call it just usually we call it 2 gigahertz or 5 gigahertz, right? But this is the real thing. It's 2.4 something, and this is 5. When we have, for example, a router, a network card, a wireless network card, we're going to say, is this working in 2.4 or 5 gigahertz? We say it's working in 2 gigahertz or 5, right? So we just maximize the number 2, but when we say 2 we mean all this, and when we say 5 we mean all this. So 5.17 gigahertz and going till 5835 gigahertz, right? In this one we have 24 channels here. If you're going to count them, you're going to find 24. Here is it. Band of 24 communication channels. In the 5 gigahertz band, we have 24 channels. And you see the length of the wave is much shorter. We have a higher frequency here, right? So more power, more energy, but less distance. Why? Why when we have low frequency, we have longer distance? Because if you imagine, but the data is always low rate, right? Everything is logic, right? So imagine I have this wave here, right? So you see, in 3 cycle, I already traveled all this distance, right? But when I have short wave, see, in 3 cycle, this is the distance that I did. So in this one, I'm going to need more power to travel all this distance, right? So the low frequency here, the low frequency are bigger for the distance, right? They have less disruption because of the wave when it meet the wall. For example, let's say this is the wall, right? Right. So I have more probabilities with the longer wave to get through it, and the disruption will be less, right? Because it's just one wave. But what about this one, right? So it if it still go here, it gonna meet the wall like this. Of course, the signal can't just go inside the wall like this, right? Especially depend on the material. We talked about all these parameters and all those properties, right? But this one have less turbulence, right? Less problems in communication. This one have more, need to be more carried, more corrected, more protected. The signal need to be more protected. One advantage of this is the data. This is a high rate data. This is low rate data. You see, in all this distance, let's say this is 10 meters, right? This is 10 meters. In here, in 10 meters with this wavelength, all I transported is 1, 2, 3. I transported 3 bits, 3 cycles. But in this one, in 10 meters, I will be able to transport a higher data rate, right? So in this one, I will have much more data in the same time, in the same distance, using more energy because I need more frequency. So you see that there is a balance in between. Each one is better than the other one. It depends on what, right? This is the difference between the transportation of data through a carrier, through wave. Okay, so we are using now both, right? Now we are using both type of networks. In Japan country, we can use channel 14. Yeah, many countries. I don't have details about the countries, but there's many countries. I don't know if in Japan especially should be, maybe here in Canada also. I don't know. Here it's 11. I saw just the 11, but it depends. In some countries we have the 14, so they use the 14. Of course, here we are talking just about this range here, guys, right? This one, see, from 2.4 to 5, right? all those channels are right here from 2.4 to 5, just in this space, right? The others are used for other things, like for example, from 9 kilohertz to 100 kilohertz, you have the radio navigation, marine and aeronautical communication, right? The marine in the ships on the on the water, whatever, planes on the space, they are here. You have the AM radio from 100 to 1 megahertz. All this is AM radio. So when you are in your car and you are listening to the radio, an AM radio, you are on this frequency, in this range of frequency. There's a lot of channels and you are just choosing from one to another one, going from 100 kilo to 1 megahertz, right? Shortwave radios, FM radios, television, all the television band here, see, L band satellite, C band satellite, cellular and WiMAX, they are here also somewhere, right? GSM and WiMAX right here. And you have the Kayo and Kaya band satellite of WiMAX also, and other satellites for science and military purpose and those stuff, right? They are all over 100 gigahertz till 300 gigahertz. Safar, 16:10 a.m. Well, I never listened it. I think it's an Indian channel, right, Chief? Okay. Yeah, it's here. It's somewhere here. Okay, so all these channels here, they are just somewhere in here, from 2.4 to 5. Safar means soulmate in Hindi. Ah, that's good. So in this radio, you're gonna find your soulmates, right? You're gonna call and meet some people and the stuff. That's good. I know that there is an Indian channel here also in the radio AM from Toronto. We had a girl that she was working on that radio on Herzing. She was a student on Herzing, I guess. She was working on that radio. I don't know if she's still in Herzing or not. Okay, so a wireless PAN. PAN is personal area network. What this means, this is a really, we studied, right? MAN, WAN, LAN, PAN, personal area network, metropolitan, local area network, and wide area network. So the PAN are really small ones. Bluetooth, for example, see, the range is really close. So from 1 to 100 meter max. 802.15.1. This is the IEEE for the Bluetooth. The NFC, near field communication, this to touch to 10 centimeters, right? Depend on the frequency of the signal, but usually the NFC is for touching. When you tap, for example, when you pay on outside on the ATM machine or debit machine, use the tap. Right now we are all using this tap technology. You don't need to enter your password, you don't need to touch, you just tap your credit card or debit card and it will work. This is the technology of NFC. When you take the metro, for example, right, and you tap your pass, you just tap it on the machine, right? This is the NFC technology. Infrared is an outdated wireless technology that has been mostly replaced by Bluetooth to connect personal devices. Infrared required unobstructed line. Try to use it on the remote, TV remote, and when you have something in between, it will not work, right? So the infrared need an obstructed line between the emitter and the reception of sight, between the transmitter and the receiver here, right? So this is the 8.802.11 legacy. That was the infrared. Now all the wireless stuff are here, but we add letters for that, right? We add letters for that. Wireless LAN, Wi-Fi, we have 800.11a, b, g, a. We have AC now also, for example. We have a lot of it, right? J, X for other purpose norms. But the main used one is B, G, and N and AC now, right? Well, B and G is still old. A, B. Well, we can say G and N and AC, but it's more N and AC now, right? This wireless, they have an architecture, so they can be in an ad hoc network. What is an ad hoc network? Ad hoc network is when you have a devices and nothing is centralized. So it's kind of a peer-to-peer communication, right? Well, this one is connecting with this one is talking with this one. So you can just have a wireless network cards in your laptops, and you can create your own ad hoc at home, right? And you connect all your devices to the same network. You don't need to have a Wi-Fi for that. Okay, you can create an ad hoc network, but there's nothing centralized here. It's just devices that they talk to each others. You can change files, you can communicate between, right? So this one and this one communicate with this one, and so go on. This is called ad hoc ad hoc network, right? Smaller wireless network in which a small number of nodes closely positioned need to exchange data. That's it, right? But using what? Using just their network card. They will synchronize in some frequency, and you can connect your laptop to another laptop, creating an ad hoc, right? So you just use Windows, for example. You can do it on Windows. You create an ad hoc, and you can connect to that ad hoc, and it's okay. You don't have internet, you have nothing, but your devices are connected. Okay. So in the wireless way of thinking and way of doing things, we have the ad hoc and the infrastructure. The infrastructure is the one that we are using for our Wi-Fi connection to the internet at home, for example. Right. So we're gonna have that central node, and the devices are connected to it. This is an infrastructure, right? We have that router here or something, but everybody, to be able to communicate with someone, he need to pass through the centralized node, right? So it's kind of a switches but wireless one. But here, if this one want to communicate with this one, he don't need to go anywhere. He just go there, right? This one can communicate with this one. This one can communicate with this one without any problem. Okay, but here everything is centralized. Everything is centralized from any direction to any direction. This is an infrastructure topology, right? Nearly all wireless network use an infrastructure wireless LAN topology, which depend on intervening connectivity device called the wireless access point. This is an app. We call it usually app for access point. Access point is the router with some antenna, right? So this is an infrastructure. This is an ad hoc. A mesh, it's common for wireless LAN to include several access points. Now we can have more complex than that. Imagine this infrastructure, but multiple time. So we'll have several access points that they are connected to each other's. Right? Access point 1, access point 2, access point 3, access point 4, and each one have his own devices connected to him. So many devices around. And now also the technology allow us to move between this access point. So imagine if I already granted my access here, and after I'm walking in the building, I'm going here. Now I'm catching the second access point, but I still connect to the same network of the company or the building or whatever, right? So this is called a mesh. This is called a mesh, more complex. So many infrastructures that they are connected together, this give us a mesh. Many infrastructure that they are all connected together, this give us a mesh. All right. Uh, what we call it, wireless mesh network, WMN, right? WMN. This one is ad or hoc or ad hoc. You can find the three notation. The infrastructure is WLAN or wireless LAN, wireless local area network. When you have a mesh, it's a WMN for wireless mesh network. Wireless one, we have WiMAX, for example, worldwide interoperability for microwave access. So this is how we can provide companies through internet from an ESP. There you go. Right. So imagine I have an ESP here. Now, instead of using fiber optic or cables or whatever, it will have some parabol with some antenna. Right. And you have this kind of communication. So it will communicate with another antenna that communicate with another antenna and so on. If it's really, really long distance, we go through satellite, right? So we're going to have some satellites orbiting the planet, and we will send the signal to the satellite, and the satellite will send it to the other curve of the other side of the planet in there, right? And we will receive it first, and after it will be distributed to the antenna, and antenna communicate with another antenna until we're gonna go to home, for example, right? So this is home here, and we're gonna send it to the home, that they will have this reception through WiMAX, right? So this is WiMAX. We are distributing, instead of having fiber optic or ADSL access or whatever, any kind of other access that we're going to see them on the third chapter. We're going to talk about the one technology. So getting access to that backbone, right, of internet through who? Through your ESP, right? And the ESP have its own network for distribution. If it's using WiMAX, so it can give, well, usually the WiMAX is used for companies, right? It's not really public. It's rare that you're gonna find a particular person who is using WiMAX. But usually it's companies that they have their access, internet access, but instead of using cables and fiber optic, they are using satellites, right? They are using satellites to get access to internet. Another technology doing the same for the same purpose, proprietary broadband wireless access in this one, right? So we use broadband for it. Or LTE. LTE now on the cell phone merged the cell phone with why we call it cellular, because you see in this antenna here, we build cells, right? We build cells in the country. And here are the nodes of the antenna. Usually they are communicating one to another 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 one. Well, LTE also used the same technology with the satellite, with whatever, to communicate everywhere from one portion to one portion. So this is an area, but this area, it's not all the world. This is just a network of one operator. Let's say, for example, this is Bell technology. But after, there is other ways to communicate through WiMAX, through other technologies, through other kind of routers, through other kind of backbones, to go to India Telecom, for example, right? And there you have, each operator have his own cells of antenna, that we call it cellular phone. Now we use also the internet through that technology. Let's call it LTE, 4G, 5G coming soon, much more complex and high speed and whatever, right? But 5G is based on satellites everywhere. All right, so wireless one outdoor, it's under the 16. But the Wi-Fi, when we say Wi-Fi, we are referring to this. That's it. We are referring to the wireless LAN. Okay, when we talk about the Wi-Fi, we talk about those things here. This is it. Okay, this is the Wi-Fi, wireless fidelity. When we say wireless fidelity, we are talking about this part here. The other are not Wi-Fi. Those are not Wi-Fi, and those are not Wi-Fi. Those are wireless technology, and this is wireless technology. But it doesn't mean Wi-Fi. Wi-Fi for wireless fidelity, we are talking about those things here. The ad hoc, the infrastructure, and the mesh. That's it. Those frequencies here. That's it. Okay, this is the Wi-Fi, the part of the Wi-Fi. The Wi-Fi or the wireless LAN standard. We started having the B, see our IEEE 11B. This one worked in the 2.4 gigahertz. It was the original one, not really the first one, because B and A was exactly invented in the same time. Okay, around the 99, they become standard, right? B and A. We have a lot of other technologies before, right? The legacy coming from this infrared stuff, the Bluetooth was working, the NFC, and many other wireless LAN older standards, right? But the commercial standard that we get is B and A in the same time. So we get one working in 2.4, and we get one working in 5 gigahertz, right? The A working in 5 gigahertz, and the B working in 2.4 gigahertz. It's much more, right? So we have 54 megabits, right? But it was really weak compared to this one. The signal need to be protected much more than this one, and I explained to you why, because of the wavelength, right? Higher debit, more expensive. This technology was really expensive, but they were in the same time, right? They were in the same time. In the same time we started A, we started B. It doesn't mean that the letter is one A after B or whatever. It's just letters, right? It's just letters. There's nothing related to the chronology of the timing or whatever in here, right? So we get theoretical speed at 11 megabits. More realistic bandwidth is 5.9. 6 megabits was the standard in TCP, 7 in UDP communication. Wow, we have here interesting things. Gear can incur interference from microwave oven, cordless phone, and other appliance using the same 2.4 range. However, by installing the B gear reasonable distance from their appliance, interference can easily be avoided. So if you have a microwave, if you have any other wave things that working in the same range, you're going to have interference with it. If it's in another range, you're safe. You're good. Okay, that was being called Wi-Fi 1. The B was being called Wi-Fi 1. The A in the same time was Wi-Fi 2. So the Wi-Fi 2 usually found on business network. So this one was targeting more the particular people. This one was targeting more the business one because they needed this higher debit for business purpose. Business company, you have more telecommunication, you have more stuff, and you are richer also, so you can get it because it was expensive at the time, the A technology, right? So usually found on business where you be better serve home market. See, so two different ones. A support bandwidth of blah blah blah. This higher frequency compared to the B shortens the range. So you see here we have shorten the range compared to the B. The higher frequency also mean signal have more difficulty penetrating walls, and I just did explain to you why here, right? Well, I deleted that. think of the wall that I was explaining here, right? So it need more maintenance, more things, more energy to penetrate those things, and so on. So have more difficulty to penetrate walls and other obstruction because of the A and the B use different frequency. They were two separated technology and they were not compatible at all, right? So if you have, for example, a laptop at the time where the network card work in B and you have an access point that it's working in A, you will not be able to connect, right? Or even devices that they have different network cards, one working in A, the other device is working in B, you will not be able to have a communication through ad hoc or whatever kind of communication. So they were not compatible. The A and B were not compatible. So two different entities, two different standards. That was called Wi-Fi 2. So compatible with each other. Some vendors offered hybrid, right? We started to have hybrid after. Now we are using this hybrid things. Of course, we still use them till nowadays. AB network gear. So instead of you having one network card, you're gonna have two networks or two different antennas working in two different frequencies. But this product merely implement the two standards side by side. This is how they started doing this. So each connected device might use one of the other. I refer to Wi-Fi 2. G, Wi-Fi 3 here. They made an update here. It was around 2002, 2003. Product supporting a newer standard called G emerged on the market. So what they did with this G, they hired the frequency, right? They still hire the frequency, but still using the advantages of 2.4 gigahertz, right? So they used the B here, they used the B and they try to enhance it to get a higher debit as the A without having all this problem of the A, the difficulty penetrating walls, the short distance of it, and so on. So they kept the advantages of A. What is the G? G mainly is the advantages of B and the advantages of A merged together. We got G, right? Of course, G, since it was working in 2.4, so it was compatible, backward compatible with B, but it wasn't compatible with A, right? So the A still orphan here by itself, okay? We got 2.4 frequency reader is backward compatible with B, but not with A, meaning that G access point, it will work with B and vice versa. Well, the problem here also, if you have a network, a wall network working with G, and you have one device that it's B inside, the wall speed gonna down to the B, right? That was a really, really big disadvantage of this G. Because if you have a network, you upgraded your network, you're good, everything is G. One device connect to that access point, one device, one phone, one whatever thing, connect to that access point, and he's using B, the older technology, it will be compatible, it will still work, but all the speed of all the network gonna go down to B. That was a mess. Pro here, supported by essentially all wireless devices and network equipment in use today. Least expensive option. Cons, entire network slow, too much. Here we go. See, too much the B. If any B device is on that network, that was called Wi-Fi 3. We got the N after. Also, sometimes no, wireless LAN was designed to improve the G in the amount of bandwidth. So we just higher the frequency using also another technology of antenna called MIMO. MIMO is multiple input, multiple output, right? Because of the antenna, one thing that we didn't say, the antenna is either sending or either receiving at the time, right? The antenna is either saving or either sending. You will never find an antenna sending and receiving in the same time, right? So the antenna is sending or receiving. Multiple input, multiple output, we can have multiple sending and receiving. So if I have multiple antenna, I can send and receive in the same time. Okay, that's the first thing. Multiple antenna mean that I can use multiple frequencies, different frequencies. I can work in 2.4 and the other antenna work in 5 in the same time. So I can use the two technology in the same time. Well, this is usually the performance of the AC that we have here at the end, but started from the N here, right? So significant bandwidth, higher bandwidth, right? Standard, it becomes standard, wide support cross device, this N here. Comes more expensive, of course, to implement. Use a multiple signal, may interfere with the nearby B-based network. It's called Wi-Fi 4. Wi-Fi 4. AC, the more standard that we are using now, is using both. Is using 2.4 and is using the 5 gigahertz in the same time. It's called Wi-Fi 5. Higher debit can go till 1 gig on the 5 gigahertz, right? 600 here, so 600 on the 2.4 now. Fastest maximum speed, best signal range on part with the standard wired connection. More expensive, improvement only noticeable in high bandwidth applications. Refer to Wi-Fi 5. Access method that we use on the Wi-Fi is avoidance, right? CSMA, CA, carrier sense multiple access, collision avoidance. And we talked about it before, right? We explained that ghosting phenomena. So this CSMA, CA is the protocol that machines or any device is using to get access to the communication. Once they are connected, it doesn't mean that they will all talk in the same time, like some people do, and they will not understand even what they are saying, right? But they need a protocol to get access to the medium to talk or to receive something, and that protocol is called the CSMA-CA, CSMA-CD on the Ethernet wired connection. On the wireless is called the CSMA-CA, multiple carrier sense multiple access collision avoidance. Identification. We use something called the SSID, Service Set Identifier, a unique character string used to identify an access point. So remember when you scan Wi-Fi's, for example, you enable in your phone the list of the Wi-Fi, and you're going to find those names, those access points, right? This is the SSID of that access point, the name of it. It's just a set of character. We call it SSID, right? Sometimes some smart people say, hack me if you can, or whatever. It's really funny. Don't hack me. I saw those kind of Wi-Fi names, right? Go away. Sometimes they swear also, right? They use weird names in there, sometimes really lovely citations and so on. This is an SSID. This is an SSID. So it's an identifier that identify the network. We have another identifier that's called the BSSID. A group of stations that share an access point are said to be part of a BSSID. Okay. Let's see, what is this? So if we have here an access point, so this access point will have an SSID. And if I have machines connected to the same SSID, they will share an identifier called BSSID. So it's the same BSSID everywhere, saying that we are connected to the same access point. We are a family, right? We are connected to the same access point. When they share the same BSSID, they will identify each others that they belong to the same access point. We have another called Extend Service Set Identifier, or ESSID. You remember that mesh that we talked about it before? Here you go, this mesh here, right? So you're gonna find SSID for access point. That's called, for example, they will share the same here, right? Called, for example, Herzing Wi-Fi in the school. And those guys, BSSID, BSS ID, they will share exactly the same because they are sharing the same access point. Those ones, they will have another BSS ID, BSS ID 2, BSS ID 2 here, because they are in different access point. So they will be identified with their own BSS ID. Now, ESS ID is something that is shared everywhere in the mesh. So this one, he will know that he is in the same mesh to this one because they will have the same ESS ID, right? So the ESS ID is a group of access point connected to the same LAN are known connectively an ESS, extended service set. BSS that belong to the same ESS share a specific identifier. You see, so BSSs, this one and this one, that they belong to the same ESS, they will work under the same identifier that's called ESS ID, right? So this is all the identifier that you can find in the level of Wi-Fi. We have the service set, we have the basic service set, and we have extended service set. Okay, this is for the name of the access point. This is what the machines share in the same access point. This is what this shared machine share with other shared machine in the same mesh with different access point. Configuration, the process. So installing such a device is similar no matter the manufacturer model. The variable you will set during installation include when you get a Wi-Fi router, well, you need to set your SSID first, right? So you're gonna name it, for example, your name or whatever. You can hide it, you can do whatever you want. An administrator password, it's very important to go and change it because usually when the ESP send you a router, it will be by default in there something admin usually, right? So you go and change it. Whether or not you use a DHCP or not, you have a DNS inside and so on, right? Whether or not SSID is broadcasted or not, so you can configure it and hide it. People will, when they scan, they will not see it available in there, right? Because of the access point is always broadcasting something called beacon packets, right? Those are beacons, and from the beacons, this is how the devices can identify the access point around them, because the access point still broadcasting those things non-stop. Security options such as which type, and for each type, what credential are necessary. Well, all the security stuff that we're going to talk about them right after. We're going to take a little break here. In the same time, I give you here two links of simulator or emulator if you want, an online emulator for routers. You see, this one is for D-Link. And if you go in there, you can find how you can set up a D-Link router, right? So this is an operational system based on the web interface. This is like Windows. This is like the kernel is Linux. This one, right? Usually in the routers, you're gonna find kernel based on Linux. OpenWRT, for example, is open source. Usually, this is what I put on my own routers to give me 100 freedom to do whatever I want inside, right? Uploading OpenWRT. This is one of the open source operational system of routers that you can use in the wild. This is D-Link. This is D-Link operational system. The firmware is called firmware version 1.4 here, right? There's many versions, many updates. And if you go there, you can find how to play with the routers and configuration of D-Links inside, right? So when we come back after the break, we're gonna see some few stuff together quickly, the most important ones quickly, right? And you have another emulator website here for all the TP-Link. You have all the models of TP-Link. You just click on one TP-Link, RC8, for example, and he will give you all the demonstration. What you have inside, how you configure it, what is the tools, what is whatever, right? So this is for home, for small businesses. There's my DHCP here on this C8, RC8. So you have all the models of TP-Link emulator here. See. Smart business, bigger. You can go much bigger, right? This is for business. You see, you have all the spots the stack, build it. VLANs, build your own VLANs here, Mac VLANs, quality of service that we talk about it, access list in the router. This is something that you're gonna SNMP also. You're gonna study on block 2 in the Cisco. But this is a really wonderful website, right? This is a really wonderful website. DSL gateways. You see router gateways, DSL, and it gives you a simulation of it. Right. You have all the simulation. It's like the real thing, so you can go and check, have an idea about it. All the TP links are in this website emulator. Right. D-Link is on the first link that I gave you here. So you guys, after, you can have time and go play with, see some basic stuff in there. We're gonna take a break, 30 minutes, and we're gonna come back at 15 to 11, and we'll finish with this part of security here.